The data center is frequently imagined as a weightless, ethereal vault. In reality, it is a collection of millions of spinning magnetic platters housed in metal racks, each one susceptible to physical degradation. Inside a hard drive, microscopic magnetic domains represent data as ones and zeros. Over time, these tiny fields lose their orientation and spontaneously flip their values, a phenomenon engineers call bit rot. The threat also comes from the sky. Background radiation pierces the atmosphere, and occasionally a high-energy cosmic ray slams into a silicon processor, physically altering a bit's electrical state. In magnetic tape archives, the chemical binders holding magnetic particles to the plastic backing absorb moisture and dissolve, leading to a total loss of signal. Data storage is a constant struggle against physical entropy. Without active intervention, hardware failure is a baseline condition of the system. For decades, the standard defense against this decay was the RAID 5 array, a system designed to reconstruct lost data from a single failed drive using parity shards. This blueprint maps the unrecoverable read error rate. For standard consumer-grade drives, there is a statistical probability of one read error every 12.5 terabytes. Modern enterprise-scale drives now hold 16 terabytes. When one drive fails in a massive array, the controller must read every surviving sector to rebuild it. For an array using 16 terabyte drives, the required read volume overshoots the statistical error limit by nearly 4 times. At this scale, the probability of a secondary read error during a rebuild becomes a statistical certainty. A single error during this process prevents the lost data from being reconstructed, causing the entire array to collapse. While parity-based backups were once a reliable safety net, the density of modern storage has made the RAID 5 protocol insufficient for large-scale data protection. The solution is found in a 1960 paper by Irving Reed and Gus Solomon, detailing a 5-page theorem that had no immediate practical application. This math was eventually operationalized for the ultimate high-stakes environment, deep space telemetry for the Voyager spacecraft. Voyager faced constant data corruption from cosmic radiation. The Reed-Solomon algorithm allowed NASA to identify and correct damaged data packets before they reached Earth. In the 1980s, the same mathematics enabled the consumer audio CD. The equation recalculated missing data from scratched disks to prevent skipping. The same mathematical continuity that protected Voyager is now the primary defense keeping the global cloud operational. To handle data at an exabyte scale, cloud providers move toward erasure coding, a system that uses matrix algebra to reconstruct lost information. This grid represents a file in a backblaze vault. The algorithm splits it into 17 data shards and 3 parity shards. Entire server racks can go offline, destroying 3 shards simultaneously. The system calculates the inverse matrix, multiplying it by the surviving shards to perfectly recalculate the missing data. Modern implementations written in Go achieve speeds of 47,000 megabytes per second, reconstructing data faster than the physical limits of the hardware. Files in the cloud are no longer stored as simple copies. They exist as fragmented algebraic equations, recalculating themselves to ensure the data remains readable, even as the underlying magnetic surface physically fails. This mathematical framework allowed companies like Google to rethink server architecture from the ground up. They abandoned the pursuit of flawless hardware, assuming instead that commodity servers are unreliable and will fail as a matter of routine. The challenge shifted to distributed consensus, ensuring that thousands of separate, failing machines can agree on the exact state of the data at any given microsecond. Leslie Lamport solved this with the Paxos algorithm. He used the analogy of a chaotic parliament, where legislators wander in and out of the chamber, yet the group still manages to maintain a consistent record of past laws. Modern infrastructure relies on this logic to function. The cloud is a software-defined layer of orchestration, maintaining data availability by treating thousands of failing physical machines as a single, resilient system.